In this lesson, we're going to start by talking about the end behavior of polynomial functions. First of all, let's make sure that we're clear on the vocabulary. We've dealt with quadratics before. We started the year off with quadratics, actually. We've graphed some cubics just in terms of translating and reflecting that parent function. But we're going to talk more about how we can predict the end behavior of a polynomial function based on its leading term. So the leading term of a polynomial is just the term with the highest degree. So the degree of a polynomial function is the value of its highest exponent and the leading coefficient is the coefficient of that term with the highest exponent. And so if the polynomial is written in standard form such that all of my exponents are decreasing as I'm looking at the polynomial from left to right, then the very first term tells you everything you need to know about the end behavior of the graph. And so you see 4 basic different ways that a polynomial function can look. So I don't want you to get too hung up on this notation because remember, they're using limits to talk about end behavior, and limits is a pre-calculus concept and we haven't talked about that. But if you were to translate what they're saying here, you could kind of cross out this word limit and say as x approaches negative infinity, then f of x is approaching negative infinity. And again, as x approaches positive infinity, then f of x approaches positive infinity. And you could go through that process for all of these. So, to clarify, if the leading exponent is odd, and its coefficient is positive, you're looking at a function that goes like this, out on the left side of your graph, and then it does stuff maybe, and it ends like this. Whereas if the leading exponent is odd, but negative, the leading coefficient is negative, then it's doing the exact opposite. On the left, it's going way up, and then it's doing something in the middle maybe, and then all the way on the right it's going down. If the degree of the polynomial is even, if the largest exponent, is even, and the leading coefficient is positive, then on the left it's going all the way up, and maybe it's doing something in the middle, and then on the right it's going all the way up. And it's doing the exact opposite if the leading exponent is even, but its coefficient is negative. It's pointing down. Okay, so I didn't want to spend a whole lot of time with the notation in this example, or in this key concept. I just wanted to kind of visually talk about how the function is behaving. But in this example, and if you're wondering why there's no example 1, it's because example 1 is just dealing with very, very basic polynomial functions that aren't really doing a whole lot, and that's, I think, kind of a waste of time for what we're trying to accomplish in this lesson. Okay, so applying the leading term test. So the way that we've been talking about end behavior, we tend to look at it as a table. So as x approaches, then f of x approaches. Well, as x approaches infinity, and as x approaches negative infinity. So this is my leading term. The leading coefficient is positive, and the degree is odd. So that is doing what this graph is doing. Notice that the degree is odd, the leading coefficient is positive, so I know on the left it's going all the way down. On the left, it's going all the way down. And on the right, it's going all the way up. And if I asked you to use the leading coefficient, the leading term test on a test to determine its end behavior, this would be adequate. Okay, similarly, as x approaches, f of x approaches notice again, this is the term I'm interested in. The coefficient is negative, and the degree is even. Well, that fits this description. Degree is even, leading coefficient is negative. That means on both sides, negative infinity and positive infinity, my function is approaching negative infinity. The last key concept I could fit on this page is that when I have a polynomial function and I know its degree, that degree tells me the maximum number of real zeros. And at most, n minus 1 turning points. In example 3, we're being asked for the number of possible zeros and turning points. So the main thing that you're focusing on, again, is that leading term. More specifically this time, its exponent. So because the degree is 3, I know that the maximum number of real zeros is 3. And the maximum number of turning points is 2. And then the instructions say determine all of the real zeros by factoring. Factoring, that's not going away. Okay, so I look at this polynomial and I realize that it has the greatest common factor of x. So f of x equals x times x squared minus 6x minus 27. And when I've factored that x out, what I'm left with inside that polynomial, or inside the parentheses, excuse me, is a trinomial. And that trinomial conveniently factors. It becomes x times x minus 9 times x plus 3. And if I set those things equal to 0, then that means my zeros are 0, because x would equal 0, 9, because x minus 9 would equal 0, and negative. First, we identify the maximum number of real zeros. Which will be the same as our degree. So it's 4. The maximum turning points is 1 less than that, 3. And then we factor it. So f of x equals, now this polynomial doesn't have a greatest common factor, But look at these exponents. This is x to the fourth. This is x to the second. We can factor this into two binomials where these will be x squareds that I multiply together in order to get that x to the fourth. And then the same thinking applies as far as the numbers go. I want two numbers that multiply together to give me 15 that add together to get 8. Well, that's 5 and 3. And then since this sign is positive, I know the signs in my parentheses will be the same. And when the signs in the parentheses are the same, they're always whatever this sign is. Okay, so x squared minus 3 equals 0, or x squared minus 5 equals 0. So x squared equals 3, which means x is positive or negative the square root of 3. And same idea here, I'll end up with x equals positive or negative square root of 5. And so my zeros are positive and negative square root of 3 and positive. You may be noticing there's a difference between my example here and yours. The difference is in the title. When I went to record this, I realized that this should have said example 5, polynomials with repeating zeros. I've already addressed a polynomial function in quadratic form. I addressed it here. Okay, so on your notes, this correctly says polynomials with repeating zeros. Okay, so first let's address the number of possible real zeros. Okay, once again, what you're interested in is the degree of the polynomial. So possible zeros. And of course, we mean real zeros. Even if I don't write the word real, please understand that I mean possible real zeros. 3, possible turning points. Is 2. And then we want to determine all the real zeros by factoring. So in this trinomial, I notice that I have a greatest common factor of, well, they all have x's. They're all even, so they're divisible by 2. And just to make the next step of factoring a little bit easier, I'm going to factor out a negative 2. Okay, so g of x equals negative 2x times x squared plus 2x minus 8. And so now that gives us a trinomial that's much easier to factor than if I had had that annoying negative sign out in front. So now I have negative 2x times x plus 4 and x minus 2. So then our real zeros are x equals 0, negative 4, and 2. First thing is identify the number of possible zeros. Okay, so possible zeros is 5 because of that leading exponent. Possible turning points is 4. It's always one less. And then factor. So f of x equals, notice that our polynomial has a greatest common factor of 3x to the third. And when I factor that out, I have x squared minus 6x plus 9. when I factor that, I have 3x to the third times x minus 3 squared. And so my zeros are 0, notice the exponent. Because 0 is a 0, because of this part where the exponent is 3, we say that 0 is a 0 with multiplicity of 3. For this one, we would say that 3 is a 0. Again, because of the exponent, we would say with multiplicity of 2. So what does that multiplicity mean? What sometimes happens when there's an odd multiplicity is you might see as it's passing through the x-axis at that 0, you might see the graph do kind of a little bit of a wobble. And when we see these on graphs, you might get what I mean by that. When we have something with a multiplicity of 2, when it hits the x-axis at 3, it doesn't pass through. I like to use the word bounce. It bounces off of the x-axis. Okay, so when we have an even multiplicity, you'll see the graph bounce. If it's an odd multiplicity, it'll go through. It might do a little dance on its way through, but the main thing that's important for our purposes of graphing is that it's going through the x-axis. It's not bouncing off of the x-axis. So we're taking all of the information that we've talked about in this lesson and putting it all together so that we can graph a polynomial function. Okay, so in part A, it says apply the leading term test. Now I'm not going to get really fancy about the notation for end behavior like we did here. I'm just interested in how does it look like? Where are my arrows pointing in my end behavior? So since this has a degree of 1, 2, 3, 4, 5. My leading exponent is odd. And my leading coefficient, notice, is negative. So that means my graph is doing this. Now, we'll figure out what's happening in the middle there, but as far as our end behavior goes, that's what's important to us. They've got the equation nicely factored for us, so it's very easy for us to determine the zeros of it. My zeros are 0, 4, and 1/3 with a multiplicity of 3. And then it says find a few additional points and then graph the function. Well, let me start by graphing these points. Remember what a 0 is. I said x equals these numbers. So these are the numbers that x equals when the graph is passing through the x-axis. So I know it passes through here. I know it passes through 1, 2, 3, 4 here. It passes through at 1/3. Okay, now it says find a few additional points. So maybe I want to figure out what this function is doing at -1. Maybe I want to find out what this function is doing. The difference between 0 and 1/3 is so small, I'm not going to do too much between those 2 points, but maybe I want to see what's happening between 1/3 and 4, and maybe I want to see what's happening at 5. So this is where the calculator comes in again. Okay, so when x equals -1, y equals 2 times -5 times -4 to the 3rd power. So, oh my goodness, y equals 640. So this has some very extreme behavior going on. It's way up, way up here. Okay, but in the interest of our graph, I'm just going to throw a point way up here. Okay, and then maybe let's see what's happening when x equals 2. So when x equals 2, I have -4 times -2 times 5 to the 3rd power. This is going to be massive, 1,000. So again, I'm just going to throw a point up here just to indicate this is getting very, very big. And finally, let's see what's happening at x equals 5. When x equals 5, I have -10 times 1 times 14 to the 3rd power. Oh my. That is y equals -27,440. So I'm going to plot a point way down here. Okay, so this graph is behaving very, very extreme. And as I've mentioned before, even though this graph is not super duper precise, I've used the information that I had access to without a graphing calculator in order to get a reasonable representation of what's happening in this graph. And I'm pulling up Desmos on my device so that I can show you how wildly extreme this graph looks. So -2x times x minus 4 times 3x minus 1 to the 3rd power. And you can see, as I zoom out of the graph, it's really, really steep. Okay? But we plotted our points where they belonged. We represented that it was getting very big and very small. And that's what I'm looking for. In part B, start the same way. Let's look at this term to talk about its end behavior. Since, again, it's odd, and again, it's negative, it's behaving kind of the same way. It's doing this. And this one isn't nicely factored for us, so we need to factor it. Let's factor a -x out of it. So I'll factor x and get x squared minus 2x minus 8, and that will be equal to negative x times x minus 4 and x plus 2. So that means my zeros are x equals 0, 4, and negative 2. Remember how we're finding these values. If this equals 0, then x equals 0. If this equals 0, then x is 4. And if this equals 0, then x is negative 2. So let's plot those. 0, 1, 2, 3, 4, and negative 2. Again, the instructions ask us to find a few additional points so that we see kind of what's happening between when I take that negative 3 and raise it to the third power. I get negative 27, but don't lose sight of this negative sign out front. That makes it positive 27. So I have positive 27 plus negative 3 squared is 9. 9 times 2 is 18. And then plus 8 times negative 3 is negative 24. So y equals 21. So that's still off my graph, but not as bad as the last one. So I'm going to, again, plot it way up here just to indicate it's getting big kind of fast. Let's see what's happening between these two zeros at x equals negative 1. So that'll make this 1 plus 2 minus 8 is negative 5. And then let's see what happens at x equals 2, kind of halfway between those zeros. When I plug in 2, I have negative 8 plus 8 plus 16. And that'll be, again, off my graph, not as extreme as the last one. I know it's going to cross through here. And let's see what's happening at x equals 5. So when x equals 5, I have negative 125 plus 50 plus 40. So that's negative 35. And so we have kind of an idea of what our graph will look like. And if I wanted to compare it to its graph in Desmos so that I know that I didn't do something massively horrendous, that's what Desmos is for. I'm having difficulty typing this in. Hopefully you're having better luck. Negative x to the third plus 2x squared plus 8x and here's our graph next to our graph, and we see that again it's kind of extreme, but we have the basic shape of the graph just about right.